Here is a habit worth breaking. People treat the loss function as a tuning detail, something you pick off a menu and move on. Mean squared error for regression, cross-entropy for classification, done.
And isn't that fine? They feel like interchangeable knobs. You try one, the numbers look off, so you swap in another and keep going. It is just a formula that turns a mistake into a number to shrink.
That is the intuition almost everyone starts with, and it quietly gets the causality backwards. That is exactly the habit, and it hides the most important decision you make. Choosing a loss is choosing a probability distribution. For your output, look at the shape every supervised network shares. The network emits raw scores. A link function maps those scores to the parameter of some distribution over the output. And the loss is the negative log likelihood of your data under that distribution. So minimizing the loss is nothing more than maximizing likelihood. Every supervised network you have ever trained is a maximum likelihood estimator. The loss is not arbitrary. It is whatever distribution you assumed, written down as a penalty. So the knob was never really a knob. It was a hypothesis about your data all along, and picking it blindly means guessing at that hypothesis. So the menu of losses is really a menu of assumptions. And the whole table follows one recipe. Name the distribution of the output, and its link and its loss are decided for you. A binary outcome, yes or no, is a Bernoulli distribution, so you get a sigmoid link and binary cross-entropy. One of several classes is a categorical distribution, so you get a softmax link and cross-entropy. A real number, with noise you assume is constant, is a Gaussian, so you get an identity link and mean squared error. A count, 0 or 1 or 17 events, is a Poisson, so you get a log link and the Poisson negative log likelihood. 4 familiar losses. 4 different bets about where your data came from. You do not pick the loss, you pick the distribution, and the loss is what that choice costs you when the data disagrees.
But mean squared error is just the regression loss. It is what you reach for when the target is a number. Where is the assumption in that?
The assumption is the whole thing. Mean squared error is not. The regression loss. It is the claim that your targets are Gaussian around the prediction, with the same variance everywhere. Symmetric noise, thin tails, one constant spread, the same size wobble whether the true value is small or large. When that picture is true, squared error is exactly the right tool and nothing beats it. When it is false, you have chosen the wrong prior and the model pays for it in data and in bad predictions. The formula never announces the assumption, it just enforces it. Now here is the fact that looks like a coincidence and is not. Take any pair on that menu and ask for the gradient of the loss with respect to the raw scores, the thing that tells training which way to nudge the weights. You might expect 4 different distributions to give 4 different, messy answers. Instead, every single time, it is the same thing, the predicted mean minus the target. The residual and nothing else. Logistic regression, softmax, least squares, Poisson regression, all 4 collapse to the predicted value minus the observed one. The distribution changes, and the direction of learning keeps the same simple shape.
That cannot be luck. Why would 4 different losses hand back the same gradient?
It is not luck. These are all exponential family distributions, each paired with its canonical link. And that clean residual is the defining property of the canonical link. You pick the distribution, the matching link comes with it, and the tidy gradient falls out for free. It is why, in the Scratch library, the backward pass is written once and reused across 5 losses without changing a line. Each loss is just 3 tiny methods, and the gradient method returns that same residual. How those gradients actually flow back through the rest of the network is its own from Scratch series, coming later. Here we only need to know that whatever distribution you assumed at the output, the signal that starts training is the same honest quantity, how far off you were. Let us make a mismatch bite. Remember what squared error believes. Gaussian noise, symmetric, thin-tailed, the same spread at every input. Thin-tailed means a point far from the line is treated as almost impossible. So if one shows up, the model concludes it must be very important. But suppose your real noise is heavy-tailed. Think incomes, or a sensor that spikes now and then, or network delays. Most points sit close, and every so often one lands far out, and for your process that is perfectly normal, not a miracle. The rare big value is part of the pattern, not a betrayal of it.
So what does squared error do when one of those far points shows up?
Watch the fitted line. Because the squared penalty grows with the square of the distance, that one outlier contributes an enormous cost, and the fit swings toward it to pull it in. One rare point drags the whole line off the crowd it was explaining. The model is not broken. It is doing exactly what a Gaussian tells it to do, treating a big deviation as a sign that something is very wrong, because under thin tails, a big deviation is supposed to be almost impossible. Believe the heavy tail instead. Switch to a heavy-tailed likelihood, and the same outlier barely moves the fit, because now a far point is expected once in a while. Absolute error, for instance, follows the median and simply shrugs it off. Same data, different assumption about the noise, a different answer. And you did not tune anything, you changed what you believe. Counts give the cleanest mismatch of all. Suppose your targets are counts, the number of events in a window, never below 0. Fit them with squared error, and you have quietly told the model 3 false things. That the noise is symmetric, that its spread is constant, and that negative predictions are fine. So it will cheerfully predict a negative rate, which is nonsense for something you can only count upward. Now switch the head to a log link with a Poisson likelihood. The predicted rate is the exponential of the score, so it is positive by construction, it can never dip below 0. And the variance grows with the mean, which is exactly what counts do. Rare events are steady, common ones swing more. Nothing about the network changed. You just stopped assuming a bell curve where a counting process lives. Step back and notice what never moved. Through everything we have done, the body of the network stayed the same. Only the head changed, and the assumption that head encodes. The network proposes the raw scores, the loss disposes their meaning. Change the loss, and you have not touched a single hidden layer. You have only swapped the story about where the output's noise comes from. That separation is the organizing idea the rest of the series keeps leaning on. Once you see the head as the assumption, 2 richer heads come almost for free. The first is the heterosidastic Gaussian. Instead of predicting only the mean, the network predicts the mean and the spread, 2 numbers. Now uncertainty is not a constant you assume. It is something the model reports, input by input, saying loudly where it is unsure.
And what if the truth is not 1 bump at all, but 2, a right answer that is either roughly here or roughly there?
Then you want the mixture density. Head, which predicts several bumps instead of 1, for outputs that are genuinely multimodal, where the average of the 2 right answers is itself wrong. It is not new machinery. It is the same idea, a richer assumed distribution bolted onto the very same body. So the scorecard for this episode writes itself, the same 3 rows we will fill for every architecture in the series. The bias, your loss silently picks the output's noise model, whether you meant to choose one or not. The win, match that model to reality, and you need far less data to learn, because you are not asking the network to discover from scratch what you already knew. The bill, get it wrong, and the network is confidently wrong, fighting the geometry of the problem exactly where you cannot see it, spending its capacity to satisfy a distribution that was never true. A loss is never just a knob. It is an assumption about the world, written down as a penalty.